Today we are going to do counting signals part 1. Let's get right to it. So let's get into it. Woo! So this first thing we're going to do when we count signals is symmetry. Okay, symmetry. Now it's not a real word anymore. Symmetry. Look for symmetry. In this case, in red, I have drawn a line of symmetry, and it's right down the middle. And what we know about symmetry is if these two methyls, for example, are symmetrical, those hydrogens, all 6 of them, are going to be one signal, and they're going to be exactly the same. That's why I wrote a 6H, because I decided to include the integration for you as well. Down here, this is also the next most obvious one. It's in the middle. Simple enough. Those two hydrogens are on the same carbon. There's no chirality or anything. So we know that those two will be the same, and the signal is 2H. Now, what's interesting is the double bond. I've already said double bond about 10,000 times in the past 10 minutes. But in this case, let's split it in half, even though the answer is already there for you. So carbon 1, carbon 2. On carbon 1, we have 2 unique groups, right? On carbon 2, we have 2 hydrogens. These 2 hydrogens are going to be diastereotopic, as I've written right here. But since we have symmetry, the 2 purple go together, or the 2 top ones, and the 2 bottom ones go together, aka the 2 blue ones. So we're going to have 2 signals coming from the double bond, and each of them are going to be 2H for their integration. So all together here, we have 4 hydrogen signals. Or let me not write it like that. 4 hydrogen signals. Moving on to the next one, we have this fancy schmancy looking benzene ring. And first thing I did, symmetry, right down the middle. When we draw this line of symmetry, we know that these 2 methyls are exactly the same. So again, we have a 6H signal. I drew this one in for you guys because everyone always forgets about him. He's all alone. There will be a hydrogen right here, and it will be 1H. It will be all by itself. This carbon does not have a hydrogen because it's a double bond. So there will only be 3 groups. Next down, symmetry down the middle. These 2 hydrogens are going to be the same. These 2 blue hydrogens are going to be the same because of symmetry, and this one will be all by itself at the bottom. So, if we count this together, 1, 2, 3, 4, 5, we have 5 hydrogen signals. Last one of this row is this one right here. It's a benzene ring with 2 methyl groups, and there's actually 2 lines of symmetry going like this. When we do that, we create essentially 4 quadrants, right? And the important thing I want you to see is 1, this carbon, again, does not have a hydrogen, so ignore it. So we're going to look at these methyls first. The methyls are going to be equal to one another. Cool, so that's 1 signal. Now, each of these 4 hydrogens will be exactly identical because it is going to be next to a hydrogen, next to a methyl, next to a methyl, next to a hydrogen. So we will have 2 hydrogen signals total. Another benzene, and I'm just finding different lines of symmetry to give to you guys. So drew the line of symmetry right here. First things first, look at those darn methyls. Methyls are not going to always be symmetrical. It just so happens that a lot of the ones that I've given you here are. And so this is 6H. The next signal is going to be this one by itself in the middle. These 2 orange ones are symmetrical. And then this one, again, all by itself in the middle of the line of symmetry. So all together, let's count. 1, 2, 3, 4. So there are 4 hydrogen signals. Next up, the last variation of this that I could think of, we're going to draw the line right here. And now there are no awkward ones that are stuck in the middle by themselves like the yellow and red were here. it's perfectly split. So these two green methyls will be exactly the same. That's signal number 1. These two red methyls are going to, red hydrogens are going to be number 2. And then these two orange hydrogens will be signal number 3. So there are 3 hydrogen signals. Next up, I decided to give you guys an aldehyde because I want to stress, if the aldehyde is drawn like this, you are responsible for knowing that there is a hydrogen there. It might sound silly, but in the pressure of the moment during the exam, you might forget. So please make sure you draw in the hydrogen. This hydrogen on the aldehyde is signal 1. We have another orange hydrogen right here, and then the 2 methyls, which are symmetrical. I gave this example to you in addition to the aldehyde because I wanted you to see that just because there's no symmetry across the entire molecule doesn't mean that there isn't internal symmetry. There is in this case. So we have 3 hydrogen signals. All right, so now what is all this mess in the corner, you might be wondering? Well, let's talk about it. And we're going to ignore this one for now because it's too complicated. We're not going to cover it. We have a cyclopropane, and one of them is cis, and one of them is trans. So, how do these cis and trans compare? Well, I tried to draw them kind of 3D for you guys. This is the cis, and this is the trans. We can see that because the methyls are pointing either opposite direction or the same. And I've already color-coded it, so you guys can kind of see where I'm coming from, just like the rest of them. But the 2 methyls are going to be exactly the same, just like we've done before, because they are symmetrical. And if you look at it, the methyl sees another methyl, a hydrogen. Methyl, hydrogen. We know they're exactly the same. Now, the next one I always look at is on the carbon attached to the methyl, we have a hydrogen, right? Those 2 will be the same because they're both attached to a carbon attached to a methyl, and they're only seeing other hydrogens. This last point is where it gets tricky. Now, the hydrogen pointing up sees 2 methyls in its area. The hydrogen pointing down sees 2 hydrogens in its space. So they are not the same. The hydrogen pointing up and the hydrogen pointing down are 2 completely different signals because of what they see in their space. However, if we're looking at the cis version of this, right, the trans version, the one up and the one down are still going to be the same because if you look at it next to a hydrogen, next to hydrogens. The hydrogen attached to, or opposite of the methyl, I should say, is still the same. Now the trick is here. Now the hydrogen pointing up and the hydrogen pointing down will actually be exactly the same. Even though they're pointing in opposite directions, the one on top sees a methyl and a hydrogen. The one on the bottom sees a methyl and a hydrogen. So the cis group will have altogether 1, 2, 3, 4 signals. But the the trans one will have 3. And I stumbled upon my words, so I'm going to say it one more time. The cis version of a cyclopropane will have 4 signals because of the 2 separate environments above and below the plane. However, the trans cyclopropane will have 3 hydrogens because since it's trans, it actually makes 2 identical environments above and below the plane.